Hello everyone, welcome to today's live broadcast, Improving Personnel Safety in Power Plants Through Rapid Generator Degassing. I'm Drew Robb, the Editor-in-Chief of Turbmachinery International magazine. I'll be your moderator for today's event. We're pleased to bring you this web seminar presented by Turbmachinery International and sponsored by Environment One. Environment One Corporation's hydrogen systems business is an internationally recognized pioneer in the field of large power generation monitoring. Since designing the first field prototypes of its generator condition monitor in the early 1970s, E1 has continued to refine and innovate this predictive maintenance technology for overheat monitoring of hydrogen-cooled and air-cooled generators. E1 has also introduced hydrogen purge gas purity monitoring products for the electric power generator industry. E1's hydrogen systems business is an ISO 9001 registered firm with a proven record in the field and a strong commitment to customer service and satisfaction. For more information, please visit e1.com. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the window by clicking on the small green icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark Help widget in the dock at the bottom of your presentation window. I would now like to introduce you to today's speaker. We are pleased to be joined by Steve Kilmartin. Steve is Director of Products and Markets for E1's Hydrogen Systems business. He's considered a leading expert in the field of generator monitoring and maintenance. Steve began his career with E1 in 1988 as an instrument specialist. His career has taken him in and around large machines and around the world for more than 30 years. Thank you for joining us today. Steve, please get us started.
Thank you, Drew. Rapid degassing or rapid purging of hydrogen-cooled generators is not a new concept. Several OEMs have been providing these systems for quite some time now. In most cases, the reason for rapid degassing is safety. However, they can also be used to save time during routine or normal outages. During this webinar, we will cover challenges in today's power industry. We will review why we use hydrogen as a cooling gas. We will discuss safety concerns with hydrogen. We will discuss the components of a hydrogen-cooled system. We will go over the purging process and then cover requirements, considerations, and specifications of a rapid degassing system. Before I start, I would like to review some terms I will be using in today's webinar. I will use rapid or emergency interchangeably. I will also use purge, degas, and fill interchangeably. The difference between degas and depressurization is degassing or purging is replacing one gas in the generator with another. Depressurization is bringing the case pressure down to zero. These systems can be automatic, semi-automatic, or of course it can be manual. These systems can incorporate solenoid valves or actuators to control the gas paths. The control of these systems can be performed by the PLC or PCS in the control room, a PLC, or in the hydrogen control cabinet. OEM stands for original equipment manufacturer, such as General Electric, Siemens, Hitachi, Mitsubishi. And Standard Operating Procedure, or SOP, stands for Standard Operating Procedure. The following are challenges today's power industry face. The workforce is getting younger and leaner. Many of the more experienced power plant workers have retired over the past 10 to 20 years. And utilities are deciding to operate these power plants with far less people than years ago. The training programs at utilities and the OEMs are not what they used to be. General Electric and Westinghouse used to have incredible training programs for new recruits, as did utilities and power plants. But they have pretty much been done away with. Time between outages is getting longer. This is a very important point. When I first got into this business, it was not unusual to have an outage and purge a generator every year, every 18 months, maybe every 2 years. Outages are now going as long as between outages, time between outages are now going as long as 10 years. And what that means is that people are not purging generators as frequently as they used to, and it is not unusual to go into a power plant and not have someone there, not have anyone there that has purged a generator before. Generator fleets are getting older, and OEM support is not what it used to be. As you read in the newspapers recently, both General Electric and Siemens are cutting back their workforce in the power market. Why do we use hydrogen as a cooling gas? Well, one reason is less windage or frictional losses. The relative density of hydrogen is 4 times less than air. What that means is that you can spin a rotor, a generator rotor, a lot easier in a hydrogen environment than an environment with air. It's much easier to spin the rotor. Better heat transfer characteristics is another reason. Hydrogen is 14 times more effective at removing heat. When you're generating power, electricity, you're also generating heat. So it is very important to remove that heat from the generator component within the parts within the generator. The bottom line is you generate more megawatts per pound of iron. A hydrogen-cooled generator, physically the same size as an air-cooled generator, can generate many more megawatts. There are currently over 10,000 hydrogen-cooled generators in operation around the world. Everyone has seen this fire triangle before, where you need fuel, air, and an ignition source for a fire or explosion. This is why there can be problems when dealing with hydrogen. Hydrogen is very explosive. When a mixture of between 4 and 75% with air, hydrogen is explosive. Hydrogen is colorless, odorless, and tasteless, which makes it very hard to detect in the event there is a leak. Because hydrogen molecules are so small, it is also very difficult to contain or seal hydrogen. And also hydrogen, some metals such as stainless steel may have issues when used in hydrogen because of what is referred to as hydrogen embrittlement. And as I mentioned before, the generator fleets are getting older, and the auxiliary equipment is getting older. Most of the auxiliary equipment on these generators is obsolete and certainly not rated to be used in a hazardous area. Also, as I mentioned before, the workforce is getting younger and leaner, and the training programs are not what they used to be. And very important is time between outages is getting longer. This is a headline from a local newspaper. I removed the name of the power plant. This death was a result of the purging process. My understanding of this incident was that the power plant thought the generator was purged properly of hydrogen. When they opened the manhole cover, the oxygen sensors on the personnel were going into an alarm. They assumed that the oxygen sensors were going off because of carbon dioxide in the generator. They decided to put a fan near the manhole cover of the generator, and when they started this fan up, it was not an explosion-proof fan. There was an explosion, and a person lost their life. What had happened is that the oxygen sensors were not going off because of CO2. They were going off because there was still hydrogen in the generator. This explosion happened as a result of not knowing what gas was in the generator. You can see from the picture that the panels on the turbine deck were blown completely off. The generator exploded. Fortunately, no one was hurt, seriously hurt, when this event took place. Again, my understanding of why this occurred was that one shift had purged the generator of hydrogen. Another shift come in, noticed that the case pressure of the generator was 0, decided to top it off, and they topped it off with hydrogen. So the generator had air in it. They topped the pressure off with hydrogen. For some reason, the explosion didn't occur for a day or two. They believe the hydrogen self-ignited, and this is a result of not knowing what gas was inside that generator. Because of the issues using hydrogen, we have added another triangle to the fire triangle. That includes using the proper equipment, having well-written and understood operating procedures or standard operating procedures, and having well-trained people. Now let's go over a hydrogen cooling system of a generator. This is a sectioned view of a hydrogen-cooled generator. The yellow lines represent the cooling path of the hydrogen. And as you can see, hydrogen circulates throughout the generator, throughout the rotor, the stator windings, the bushing and lower leads, the retaining rings. So hydrogen is throughout the generator. The yellow circles are the hydrogen seals between the generator case and the rotating field. There are 2 seals located on each end of the generator. Proper operation of these seals are critical not only during normal operation of the generator, but also during the purging of the generator. This is a sectioned view of a hydrogen seal. You can see that the top left-hand circle, this is the seal oil being fed to the seal. It's being fed at 95 psi, a pressure of 95 psi. The oil comes in contact with the rotor, the shaft, and it divides and goes in two directions. Because the hydrogen in the generator is 90 psi, the oil coming in at a higher pressure will flow through the hydrogen, and it will also flow towards the air side of the generator, creating a very effective seal. When operating properly, the oil creates a seal that is capable of enclosing, keeping hydrogen inside the generator. This is a typical hydrogen auxiliary system P&ID. The circle on the right is the gas manifold, which is used to put gas in and take gas out of the generator, and used to maintain hydrogen pressure during normal operation. And the circle on the left is the generator gas analyzer, which is used to monitor gas purity during normal operation of the generator and during the purging of the generator. The gas manifold is what would be modified to incorporate an emergency or a rapid purge system. This is a picture of a hydrogen auxiliary skid. We refer to it as a gas station, which contains the components called out in the P&ID of the previous slide. The generator gas analyzer portion is the right-hand circle on this picture, and the gas manifold is the left-hand circle. Now let's break down the individual components of the hydrogen system P&ID. Here we can see two circles. The one is the CO2 supply, which is connected to the hydrogen auxiliary system. This CO2 supply you can see on the circle on the left-hand side. We are monitoring the pressure of the CO2. We give a local indication where we have a gauge, and we have a pressure transmitter that is sending a 4 to 20 milliamp signal back to the control room. The connection for all the gas supplies and the feeds to the generator are on the top of this cabinet. You can see there's some flanges on the top. Those are the supply gases and the feeds to the generator. This is a CO2 tank farm. This is a non-hazardous area. One way you can tell that from this picture is in the upper right-hand corner, you have a space heater, and you would never see a space heater of this design in a hazardous area or where there is hydrogen. Another supply gas is the hydrogen that comes into the skid. We also, with the hydrogen, we will monitor the pressure, supply pressure. We will give a local indication, and we'll also again have a transmitter that will send a 4 to 20 milliamp signal back to the control room so that they know what the CO2 pressure and what the hydrogen pressure is at the skid. This is a hydrogen tank farm. Surrounding these hydrogen tanks is a hazardous area. Depending on the country, will depend on what the distance is. In the U.S., it's typically 3 meters from the hydrogen source is considered a hazardous area. These tanks are mounted outside, which is preferred because you cannot get an accumulation of hydrogen. You can get hydrogen, can be supplied from a bulk supply system, not only a tank farm, but a bulk supply system, or an on-site hydrogen generator, which is seen in this picture. We have another connection that comes inlet to the manifold, which is the air supply. The air supply will be, it's usually connected to a clean, dry instrument air system. A very important part of the gas manifold is this removable spool piece, which is used to minimize the chance of hydrogen and air being put in the generator at the same time. I use the word minimize because even with the spool piece, it is possible to put air and hydrogen in the generator, which would create an explosive mixture. You can see that this spool piece will connect to the air or hydrogen, but it will not connect to both. This circle is the spool piece. These spools are bolted, gasketed flange connections that can be removed to either connect to the air or connect to the hydrogen, but again, not both. And then we have the connections from the manifold that go to the generator and the distribution pipes or headers in the generator. We have one line for hydrogen and air, another line for CO2, and then another line that will serve as a vent. These are the connections in the generator. The lighter hydrogen will be fed through the top distribution pipe, and the heavier CO2 will be fed through the bottom distribution pipe. Both these distribution pipes will serve as a vent depending on the gas that's being fed into the generator, meaning that if I'm feeding CO2 through the bottom header, the heavier gas, then the top hydrogen distribution pipe will serve as a vent to allow the air to go out. And if I'm putting lighter hydrogen in the top distribution pipe, the bottom carbon dioxide distribution pipe will serve as a vent. This circle is the generator gas analyzer portion. You have one analyzer in this particular P&ID. Some P&IDs or some cabinets will have redundant analyzers. This analyzer also has a pressure gauge to monitor case pressure. It has a case pressure transmitter, which will send the signal back to the control room so they're aware of what the case pressure is. It also has a gauge to monitor the fan differential pressure, and again has a transmitter that will send a signal back to the control room. This is a picture of the generator gas analyzer again. During normal operation, the inlet of the generator gas analyzer will be connected to the generator fan pressure tap, and the outlet will be connected to the generator fan suction tap. the fan differential pressure will create a flow of hydrogen through the analyzer, resulting in a continuous real-time reading of the hydrogen purity. Now the rotor has to be spinning at full speed in order for this flow to occur. These are the connections from the analyzer to the generator during normal operation. Again, the inlet of the analyzer is connected to the generator fan pressure, and the outlet or return is connected to the generator fan suction. During the purging process, the generator gas analyzer will be connected to the gas manifold vent. Proper connection of the generator gas analyzer during normal operation and during the purge process is critical, which I will explain later in this presentation why it is critical. As I mentioned earlier, these distribution pipes or headers are used to fill and vent the gas in the generator. It is very important that the gas analyzer be connected to the headers that is being used as a vent when you are purging the generator. And I can't stress this enough that it is critical where that analyzer is connected during the purge process. I'm going to go through one step of the purging process to demonstrate how one gas in the generator is replaced by another gas. This is a simplified example of the purging process. Let's assume that this generator just had some work done on it and it is going to be put back online. For this demonstration, we will use CO2 as a purge gas. The first thing we wanted to do is run an air test on the generator. So what we're going to do is connect the air supply, which you can see down in the bottom right-hand corner. We open the isolation valves that will allow air to flow into the generator. Now with the air, in running a pressure test, the air can be put in either header. And I've seen P&IDs that have both. Now you can see that the generator is being pressurized with air. Now the generator already had air in it, so we're just pressurizing the generator. When we pressurize the generator with air and close the isolation valves to run the pressure test, the valve on the far left-hand side, that is the GFP, which it's not labeled on this, but one of those analyzer return lines, yeah, it is labeled GFP, the generator fan pressure, that valve may actually be opened during this test so that they can use the case pressure gauge located in the hydrogen cabinet to monitor the pressure of the generator during this test. Once the generator has passed the air test, we are going to put CO2 into the generator. So we remove the air spool. We connect up not only the CO2 but the hydrogen line. We open the isolation valves to allow CO2 to come in on the bottom header because it's a heavier gas. And we open the isolation valves to the top header to vent, to let the lighter air come out of the top header. The one thing I mentioned earlier, that it's critical to have the analyzer connected at the right point when we are purging the generator. During normal operation, the analyzer would be connected on the left-hand side on the analyzer feed and analyzer return. That's where we would connect it during normal operation. You'll see from this demonstration that when we first put CO2 in the generator, CO2 being a much heavier gas will, if the analyzer was connected at that point, would see CO2 immediately, even though there's still air in the generator. That is why it is critical that during the purging of the generator, the analyzer be connected to the vent line, and you can see that connection on the middle right-hand side where you have the vent. Underneath that, you have the analyzer purge connection. So now we'll put CO2 in the generator. And again, the heavier CO2 will be fed through the bottom header or distribution pipe. And if I did have the analyzer on the normal operation connection, it would see CO2 right now, even though the generator still has air in it. Only when the generator is completely filled with CO2 will the analyzer connected over at the purge connection see pure CO2. Now we've got the generator purged of air, filled with CO2, and now it's safe to put hydrogen in the generator. So we will shut the CO2 supply valves. We will open the H2 supply, hydrogen supply, and we'll start putting hydrogen in the generator. Hydrogen being light will come in through the top header or distribution pipe, and it will force the heavier CO2 out the bottom distribution pipe. And again, you can see that once the generator is completely filled with hydrogen, that's when the analyzer will see pure hydrogen. Once that is done, once the generator is filled with hydrogen, we know there's no air in the generator. Now we can start the generator. So we'll open our valves. We will change the position of the analyzer to go over to normal operation, which is the hydrogen feed and the hydrogen return, and we'll start the generator. That would be during normal operation. Now I'm going to skip the purging of the hydrogen from the generator. It's just a reverse of what we just did. This slide shows where you would make a modification to a existing manifold or in a gas station. What you can see here is that we would add a solenoid valve to the hydrogen supply. We would add a solenoid valve or actuator to the vent line, which is the bottom circle, and we would add a circle or actuator or solenoid valve to the CO2. So let's say, for instance, we were going to do an emergency degas of a generator. We would shut the valve on the top, which is the hydrogen supply. We would open the valve on the bottom, which goes to vent. We would use that same header, which go to vent, and then we would open the CO2 solenoid valve and allow CO2 to flow into the generator. The following slides are questions that need to be answered if you are going to incorporate an emergency purge system or a rapid degas system. You need to know what the volume of gas is in the generator, how much gas you have to remove during a purging. You need to know the size of the piping, both for the supply of hydrogen and CO2 in vent and the size of the piping that is supplying CO2 and hydrogen to the generator. You need to know the number of valves and what the orifice size is of these valves, because that could be a restriction in the flow of the gas. You need to know the number of bends that's in the piping, and you need to know the length of the piping. All of those first two bullet points are what are necessary in order to determine purge time. Then you have to determine, do you want to do a blanket purge or do you want to do a flooded purge? And what do I mean by that? What I mean with a blanket purge is when, for instance, you put in a heavier CO2, it will maintain a layer or level between the CO2 in air and CO2 in hydrogen throughout the purge process. You may choose to flood it where you're just overwhelming the generator with your purge gas. So you're not interested in maintaining a blanket. You just want to get rid of the gas in the generator as quickly as possible. One thing that is critical that I believe I mentioned before, you want to make sure that you maintain the seal oil differential pressure during this purging, because the pressure in the generator is going to be changing. And as the generator in the case of the changes, you want to maintain the seal oil differential pressure while that is happening. You need to determine what gas you're going to want to use during the purging of the generator. It is very common in the United States to use carbon dioxide as a purge gas. However, you will find throughout the world that this is changing. Some European countries are starting to use argon or nitrogen as a purge gas instead of CO2. Now, if you are going to use CO2 as a purge gas, the one thing that you have to remember is that if you rapidly put CO2 in the generator, you could cause thermal shock to the generator, or you could cause pipe freezing in the CO2 line. So you may need to use a CO2 vaporizer or CO2 heater during the purging of the generator. And then you need to know, how are you going to control? How do you want to control this purging process? Is it going to be a rapid purge? And again, a purge is replacing one gas with another gas. Or are you going to do a rapid depressurization? And that would mean taking a case pressure, for instance, that is 30 or 60 psi and bringing that down to zero. Why would you want to do that? The reason for doing that is that if the pressure in the generator is the same as atmosphere, essentially zero, then you have less likelihood of hydrogen escaping out of the generator in the event that the seals fail. So you may choose to want to do just a depressurization, or you may choose to do a rapid purge. Do you want this purge? How do you want this purge controlled? Do you want it automatic? Do you want it set on conditions to do an automatic purge? Do you want it to be semi-automatic, so where you might have operator involvement, have some automation, but then also have some operator involvement in the purge? Or do you want it to be completely manual, in that the operators will make the decision whether to do a purge or not. If it is automatic or semi-automatic, is it going to be controlled by the DCS? Is it going to be controlled by a PLC? Or is it going to be controlled at the hydrogen skid itself? And then you need to decide the portion of the piping that will shut down the hydrogen, open the CO2, and open the vent. Are those going to be solenoid valve actuated, or are they going to be actuated with an actuator? And there are pros and cons to both. I prefer actuators because they can be done. If there is a loss of power, actuators can be manually actuated. Considerations when you are deciding how you want to incorporate this. The purity analyzer connections and settings. Do you want to have the switching of the purity analyzer from normal operation to purge to be automatic by solenoid valves? Some plants decide to use a dedicated analyzer for the purge process and a dedicated analyzer for normal operation. You're going to definitely want to monitor your case pressure to make sure that you're maintaining the correct differential with your seal oil pressure. You want to make sure that you're monitoring your hydrogen supply pressure to make sure that you're not only monitoring it, but also knowing that you do have enough hydrogen on hand to fill the generator. More importantly, you want to make sure that you have enough CO2 on your plant to purge a generator. And not only the generator that you're working on, but also any generator that is on site. Because if you're doing work on a generator and you're purging that generator with CO2 and it's the only CO2 you have on hand, and you have an emergency with another generator, you want to make sure that you have enough CO2 on hand to do all of the generators that are on at your site. There's a variation in the fleet design. There's variations in the manifold designs, and you have to take that into consideration if you're going to incorporate a manual or an automatic purge system. And if you do incorporate a rapid purge or emergency purge system, then you're going to want to change your standard operating procedure and operating philosophy. So they will have to be rewritten. The standard operating procedure and operating philosophy will have to be rewritten. In summary, hydrogen is an excellent cooling gas. And as I mentioned earlier, there are over 10,000 generators in operation around the world that are using hydrogen as a cooling gas. And for the most part, these generators are being operated safely. The purging process is a critical operation, and there are safety concerns when dealing with hydrogen. We reviewed the different components of the hydrogen system and what takes place during the purging process. And we ended by discussing requirements and considerations that need to be addressed before incorporating a rapid purge system. In closing, remember, it's all about safe and efficient operation. Now I'd like to turn it back to Drew for questions and answers.
Thank you, Steve, for such an informative presentation. Before we get started in the question and answer session, I'd like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. We'll try to answer as many questions as we can. And our first question is, how in the overall picture for generator operational safety, and does this fit in with a proper hazardous location electrical classification for a generation facility?
I believe that if they're asking about the emergency purge system or rapid purge system, you have to take that into consideration, the hazardous location into consideration when you're initiating or deciding to use this type of a system. And yes, it does come into play that the actuators, the controls, the analyzers, the cabinet, the hydrogen control cabinet, all of this stuff is being used in a hazardous location, and all of it should be designed to be used in a hazard. All of the equipment should be designed to be used in a hazardous location. And if possible, all of this equipment should be third-party certified to be used in the hazardous location.
Very good. Next question. How often do you need to change the sealing oil?
You know, I really can't answer that question. I know hydrogen, and I know that the seal oil is used to be to keep the hydrogen inside the generator, but unfortunately, I'm not aware of how often the seal oil needs to be changed. However, I will be able to get an answer for that question and will follow up with the person who answered that question on what the recommendations are.
All right. The next question might be the same. It's asking what kind of seals are on the generator. If that's one that you can't immediately answer, we'll just move on.
I think I can address that a little bit. I know there are different OEMs will have different seal designs depending on the generator, depending on the model of the generator. As a matter of fact, I know, for instance, a GE Frames 7 generator actually has two different seal designs. It has one that's called a fixed seal or a bolted seal, and then it has a design that actually floats, and it's called a floating. I also am aware that Siemens has a very tight tolerance seal that uses less oil and is more effective at sealing hydrogen inside the generator. So I guess the answer to that is there are many different kinds of seal designs that are used on generators.
Very good. Next question. Is it true that hydrogen fires are invisible to the naked eye?
Yes, they can be. I actually have a picture of a recent fire of a isolation valve that developed cracks, and although the flame was visible in the picture, my understanding was that it was nearly invisible to the naked eye. I can remember once I was at a refinery where they generated their own power, and there were two stacks that were going up in the air in the distance, and one of the stack you could see a clear flame come out of. You could see a flame coming out of it during the day, and the other stack there was no flame coming out of it, or at least there appeared no flame coming out of it. And I asked this to a guy, and he said, wait till this evening and look at it again. And the flame that was coming out of that stack was a hydrogen flame, and during the day, in the daylight, you could not see it.
Okay, good. Next question. We'll get quite a few questions coming in. Can existing gas manifold systems be modified to have emergency purge capabilities?
In most cases, yes. As I indicated in one of the slides, the main change is to add a solenoid valve or a actuator to the hydrogen supply, the CO2 supply, and the vent from the headers. We are currently working on a project where we are modifying existing gas manifolds so that they can incorporate emergency purge. So the answer to that, in most cases, yes.
All right, good. Next one, can the connections to the generator gas analyzer be switched automatically for an emergency purge?
It is possible to switch it automatically. Environment 1 has designed packages where this is done. I do have to say, in most cases where emergency purge systems are used, that they will use a dedicated analyzer for the purging process that is piped into the system, piped so that it cannot be used in another system. It is dedicated for the emergency purge.
All right.
But you can switch it if you like.
Okay, good. Do you have special requirements for valve stem packing and body materials for the hydrogen lines?
Absolutely. You have to make sure that all valves that are wetted, meaning that they're touching hydrogen, that the packing and sealing and gasketing material that are used, and the metal itself, is rated to be used with hydrogen. I know one of the materials, Viton is one of the O-rings that are rated and can be used with hydrogen, but any wetted part that comes in contact with hydrogen needs to be rated to be used with hydrogen.
All right, thank you. Next question here. Does the seal oil pressure need to be controlled or regulated during an emergency purge?
Oh, absolutely. That is critical. And to give you an example, that, say, a generator that operates at 60 psi and the seal oil pressure is regulated at 65 or 70 psi, when you purge that generator, the first thing you're going to do in an emergency purge is you're going to bring the case pressure down from, say, 30 psi down to 5 psi or lower, so that you want to make sure that that seal oil pressure comes down also. Otherwise, you're going to flood that generator with oil. You'll just shoot so much oil into the case of the unit. So it is a critical step to make sure that the seal oil pressure is regulated during an emergency purge.
Very good. Who would usually control or initiate an emergency purge?
It's usually controlled by an operator. Most power plants want the operators to have control of this. So what they will do is they will have certain conditions that need to be met. To give you an example, if a power plant has a policy where during the storm season, during the hurricane season, that personnel cannot go out onto the turbine decks, which in some cases are open turbine decks. So they have a policy that personnel cannot go out there. They want that control of that purge to be done by the operators themselves. Now, there are other conditions that may occur that will, for instance, if you lose your seal oil pump, you may want to do an emergency purge. Very rarely will you see the control of a rapid or emergency purge completely automatic.
All right, very good. Next question here. Can new generators be ordered with a rapid or emergency purge feature?
Yes. I'm quite familiar with General Electric, and we happen to supply equipment to General Electric. And General Electric has ordered systems from us that do have the rapid or emergency purge features. And just for information, on those systems, they chose to use actuators as the switching devices versus solenoid valves, and control of those emergency purge was semi-automatic in that the control system would give operators a notification that they should do a rapid or an emergency purge, and then but it would be the operator who would actually actually initiate the purge.
All right, good. I think we've got time for one more question here. So, why is hydrogen considered as an excellent gas for cooling?
As I mentioned earlier, and I think it's very interesting that some person had an idea that let's use hydrogen as a cooling gas when it's very explosive. So you're putting this gas that's very explosive into a device that has potential for arcing and sparking. Anyways, whoever decided that, it works. The reason being is that hydrogen being far less dense than air, you can spin the rotor much easier, meaning it takes less horsepower to spin that rotor in hydrogen than it does in air. And also, as I mentioned, the heat transfer characteristics of hydrogen are far greater than that of air, meaning you can remove the heat that is generated when you're generating electricity from those components, windings in the generator as it's operating. So hydrogen is also excellent at removing heat.
Thanks, Steve, for answering those questions. Unfortunately, we're out of time. I want to thank the audience for attending and for participating in today's event. I'd also like to thank our sponsor, Environment One, for making today's educational webcast possible. The webcast will be available for on-demand viewing through July of 2019. You will receive an email from Turbmachinery International alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. Thanks to you all for joining. We'll see you next time. Goodbye.